All right, ladies and gentlemen, class recording has started. So, here's what I want to do today. As far as heat transfer goes, the first thing I want to do is go over a couple of definitions, and then I will give you a scenario, and I want you to apply the definitions that we talked about to that scenario, and we will use that scenario then to explain things from that point forward. Okay, so I'll explain it in more detail as we go along. But last week we introduced three terms: heat, temperature, and thermal energy. Let's talk about temperature first, right? What does temperature tell us about a substance or an object? What does the temperature tell us? Delvin, go ahead. It could, that's a specific temperature, but in general, what did we say the temperature tells us about? Kinetic energy of the particles. So how quickly do the particles of that substance move? Or how much kinetic energy they have, right? Thermal energy takes it one step further. And it's not just the kinetic energy of the individual particles, it's the kinetic energy of all the particles, right? So we talked about on Friday the difference between temperature and thermal energy as it relates to like a sparkler, right? The little sparks that come off the sparkler. That each of those individual sparks has a high temperature, but they don't do a whole lot of damage because they're so small. So yes, they hurt, but they're not going to like burn your whole hand off, right? So temperature deals with individual particles. Thermal energy deals with all of the particles that make up an object. But then the last term, which was actually the first term that we introduced, was heat. And if you look on your outline that says heat transfer and thermodynamics up at the top, heat is the first thing that shows up. So it says heat is the transfer of blank. So what are we transferring? Thermal energy. And from one object to another because of what? Temperature difference. So thermal energy will flow from objects that have different temperatures. Specifically, which way does thermal energy flow? High to low, right? So we talked about that hot objects cool down, cool objects heat up until what? The same temperature, and we call that thermal equilibrium, right? Thermal equilibrium. There's other kinds of equilibrium, but yeah. All right, so today we talk about how that happens. There are three ways that energy can flow from one object to another because of the temperature difference. So here's what I'm going to do. I'm going to give you the three definitions right off the bat. And then, like I said, I'm going to give you a scenario, a situation that I want you to apply those definitions to. So let's start with the definitions. The first type of heat transfer is called conduction. Roman numeral 2. Okay? So Roman numeral number 2, conduction. The transfer of thermal energy with no transfer of matter. Transfer of thermal energy with no transfer of matter. And there's one requirement for conduction to occur, and that's that there has to be contact. There has to be particles touching in order for them to transfer that thermal energy from one to the next. Okay? All right. Good there with conduction. We got our definition? Okay. Next, slide down to Roman numeral number 5, I believe. And the next type of thermal energy transfer is called convection. Okay. Convection is defined as the transfer of thermal energy when particles of a fluid, and fluids is a general term that we use for liquids and gases, right? And if you think about it, liquids and gases have something in common, right? Their particles are allowed to move. They're not stuck in one particular spot. when particles of a fluid move from one place to another. All right. Good with convection. We'll get to that in a second. But then for this, I'm going to save the examples because I want us to apply these definitions to a situation, because then the examples might make a little more sense. Okay. All right, and then finally on the back side, we have radiation. Okay, so you flip over to the back side. Okay.
Why is it like that X-rays are like, this is not the case. Like, why is it that X-rays are like dangerous?
So, well, let's talk about what radiation is first, okay? So, radiation is a transfer of energy by waves that move through space. There is no matter that is required to transfer this energy. The energy just goes from here to there. The waves carry it, and the waves are basically the energy. Sunlight is an example of radiation, right? There's nothing between us and the sun, but the energy still gets here, right? So, Jafar, to answer your question, okay? You asked about X-rays, right? And we talk about X-rays being dangerous radiation. X-rays are energy, and our definition of energy is the ability to do work. Well, let's go more with the ability to move, change things, do damage, whatever, right? X-rays actually carry a lot of energy. So they have a lot of potential to do damage, right? Sometimes that's good. Like, they have enough energy to penetrate the soft parts of your body, but not your bones. So we can see what's going on with your bones without having to cut your skin open, right? Or if somebody is going through radiation treatments for cancer, okay? A lot of that are X-rays, some a little bit even higher than that, energy-wise. Those X-rays kill the cancer cells, okay? So that's good. But those high energy rays, the ability to do a lot of damage, they can't tell the difference between bad cancer cells and good person cells. You know what I'm saying? They kind of kill everything. So that's why when people get radiation treatments, one, they only get a very short amount of radiation, like a very small amount of time, like seriously, like seconds at a time. So people who go through radiation treatments for cancer, they like show up at the clinic, they're there for like half an hour every day. It's just like, boom, that's it, you're done, go, right? Because we can't expose them to a whole lot of radiation, right?
Like daily too?
Yeah, because they're trying to kill those cancer cells, right? But also too, if you're exposed to prolonged X-rays, that can kill your cells, but it can also, remember, energy is the ability to cause change. It can also change your cells.
So what if this one you could go into a different...
So the change in your cells can be a change in their DNA, right? And that's what we call mutation. But DNA, hopefully you remember, DNA is what tells the cell how to make a new cell, right? So DNA tells a cell to make a new copy of itself. But if some energy, like an X-ray, changes the DNA, now it doesn't make the cell that it's supposed to make, right? So, and then it still changes, it still makes copies of itself, but it's not making the correct copies of itself, right? So if you have liver cells that get mutated, they don't make liver cells anymore. Does that make sense? Well, the mutation could be good. Sometimes that's how we adapt to things, right? But generally that happens over generations, right? If your liver isn't making liver cells and it's making something else, now your liver doesn't function properly. You know what we call that? Liver cancer.
Yeah.
Cancer is the uncontrolled reproduction of cells, but they're not the right cells. Does that make sense? Either through disease or through exposure to radiation, like energy, you cause a change in the DNA, Or it could be a chemical change like smoking for lung cells and things like that. And so now your lungs don't make lung cells. They make copies of themselves because the DNA is mutated. It's not the right copy. Does that make sense? So we want to kill those cancer cells so they stop mutating, so they stop reproducing.
But then you kill other
You can kill other cells too. So people who have radiation treatments sometimes will get like almost like a sunburn, like depending on where it is on their body, because the radiation goes into their body and kills those cancer cells, but it's got to pass through the skin cells along the way. So sometimes, yeah, they'll get like almost like a sunburn because that's basically what's happening to them. So, does that make sense?
Yeah.
But getting back to this, right? That's also like when we get a sunburn, right? That energy comes from the sun. But there's nothing in between the sun and us to take it there. It's just the energy just goes right from there to there. Does that make sense? Yeah.
So how does sunscreen end?
Sunscreen
Just like actually
absorbs that energy
just like
instead of your cells absorbing that energy, basically. Does that make
is that why you
sense?
have to put it on like over and over?
Yeah, because after a while it
Goes away.
yeah, goes away. So,
It's like a shield.
yeah, basically like a shield. Hence it's sunscreen. So.
So you should ask him about the robot thing.
All right. So let me give you a scenario. Okay. So let's take a trip. Okay, a virtual trip to a farm. Okay. So here's the grass, and here's a barn. Okay. These barns have like those crosses on the doors like that. You know? Okay, so there's the big red barn. Did anybody read the Big Red Barn when they were a little kid?
I did.
The Big Red Barn and the Great Green Field.
Yes.
Big red dog.
What?
Big red dog.
The big red, like Clifford, the Big Red Dog. So.
Oh.
All right.
That's my favorite.
And
Disgusting.
so, and unfortunately for the farmer and for the stupid cows that are inside, right? A fire starts.
No. Chicago Fire.
Like the Great Chicago Fire, if you want to think of it that way, you can. All right. So there's the fire. Okay. It's like shooting out of the top barn. Okay? Now.
Shooting had top shooting from outside already.
Say again.
Shooting had top shooting from outside already.
Fire goes up. So
Fastest spread.
it does. All right. But luckily for the farmer, he has a pond on his property. Okay? What? There you go. All right, and so here's the farmer, right? Okay. And also, luckily for the farmer, he lives in a small, close-knit community. And when one person in the community has a problem, everybody comes to help, right? So all the townspeople come to help out the farmer, right? And they bring their buckets with them. Okay? All right, so here's what I want you to do. This situation we can use to illustrate the three types of energy transfer that we just introduced. Okay? So here's what I want you to do. First, let's analyze the situation. Okay? Remember, this is a representation. It's not the real thing. Okay? What plays the role of energy in this situation?
The people doing stuff.
The water.
The water is the energy. Why? Because what does energy do? It has the ability to what?
Do stuff.
Do stuff. What is the stuff that we're trying to do?
People are also doing stuff so they can feed the
What is the stuff we're trying to do in this?
Put out the fire.
You're trying to put the fire out.
Save the cows.
What has the
Fire.
You're just trying to
stuff
save
is
the
a
cows.
general term, right?
Yeah.
What we want to
We can
make
all do
something
stuff
happen.
with this picture.
You're trying to save the cows.
Apply the definition to this. Okay, that's fine. The farmer could run away. That's doing stuff, but that's not going to help his stupid cows, right?
They're
Well, how
stupid,
about you
but
ask
it's
what
more
The
Let them
scenario.
burn it. Let them burn its cooked meat.
Well, you can't go into the fire.
It's bird meat. So,
What does it mean?
all right. So in
I
this
have suggestions
case,
to the farmer.
no, I'm not even going to introduce this discussion right now. All right. In this case, the water is playing the role of energy. In order for us to do the stuff that we need to do, put out the fire, the water needs to get from the pond to the barn. Okay? So, based on the three definitions that we just wrote down, talk to the person next to you, and let's come up with examples of how we illustrate those three principles in this situation. All right? I'll give you a couple minutes, then we'll come back and talk together, all right? Talk to the person next to you. How do we illustrate those three things in this scenario?
Maybe they can't afford buckets.
All right, ladies and gentlemen, we are back. So, let's discuss this scenario and how it applies to the three types of energy transfer. Okay? Anybody want to give me their example? One of their examples that they discussed? That was good.
Radiation of the water.
Okay. What has to happen in order to the water in order to illustrate radiation in this case?
It needs to be put on the fire.
How are
It
we?
needs to travel through the bucket. In the bucket. Through the
Nope.
Yeah.
Because the buckets, right? This is this is something moving the energy from here to here. All right? So, do you want to give your ridiculous scenario?
Oh, the radiation?
Yeah.
Oh, yeah.
Okay, so here's Jason's ridiculous scenario of the radiation. It's actually right, but we'll illustrate why. Okay, go ahead.
So you drop a bomb in the pond.
Are you serious?
Yeah, that can
Well,
make waves. That can make waves.
Okay, you can make
It's
a wave and then
it's not
splash
hard.
onto the fire, hopefully.
No,
Yeah.
saying it'll blow it up. It'll go in the air like rain,
Right.
fall in the fire.
So,
Right.
bomb
It'll be radiation
explodes,
that's going
right?
through
That's
the air.
And then the water goes like this.
That might not put out the fire.
It might not.
It might not. You also might
And
put out the fire with buckets.
before we even started this, Stephen threw out the idea of the tsunami. All right. Those both illustrate radiation. We are getting the energy from here to here. Is anything actually carrying the energy from the pond to the barn?
The explosion.
Nothing.
Well, the explosion,
Nothing
right?
really.
But is there any people there to carry the energy from here to there? This illustrates radiation. Or if we want to do maybe something a little bit more like, realistic, if we had a hose or a pump that could just spray the water from here to here, sprinkler, that might not produce enough. It might not get enough water there, but that would be radiation. Okay, because nothing's taking the water from there to there. The water's just going. Okay, very good.
Would rain?
Rain could be an example of radiation. Although to kind of illustrate, to keep it within our scenario of heat transfer, we're trying to get this water from here to here. You know what I'm saying? This would, like, Maddie, if we get it back, this would be a high temperature. This would be a low temperature, even though I know fires aren't low temperatures. But remember, heat flows from high to low, right? So that would be like bringing it back to what we're trying to illustrate here. Does that make sense? Rain would be technically getting the water to the fire, but it's not technically taking the water from the pond to the fire. Okay?
But wait, the pond, this water evaporated and it went up
Yes.
in the cloud and came down, so it technically
Either way, it's a ridiculous scenario.
All right.
Hey,
So
Steve,
that's
Steve, mental light on
radiation.
fire for-
hey, that's radiation. Okay. All right, Maddie. Do you want to explain how we talked about conduction while we were walking around?
Yeah.
Okay. Go ahead. So.
Okay, so we said that the connection was like the people, if they were like standing still and just kind of like moving the buckets back and forth.
So, in order for conduction to occur, right, the bucket starts here at the water. We fill up the bucket with the water, And then we pass the bucket from this person to this person to this person, and then that person throws it on the fire. Okay? If we look at our definition of conduction, transfer of energy without the transfer of matter. So water is playing the role of energy in this scenario. What's the matter? The bucket, or more, I'd say probably more the people carrying the bucket, right? So, but yeah, because that's what's taking the energy from here to there. But if we just pass the buckets along, people don't go anywhere. They stay in the same spot, but the water ends up moving along down the line. Okay? Does that make sense? As far as conduction goes, how that illustrates conduction. All right, convection. What has to happen in order for convection to occur? Nope. No heat. Water. The people passing the buckets, that's conduction, because we're passing the water without the people. If you look at your definition of convection,
The water on the fire.
how does the water get to the fire?
Are we talking about
The people, though, but what do the people have to do now? That's conduction.
Have their buckets.
Give me a break. They have to see the water. I don't know.
So, if you look at your definition of convection, it's a movement of a
Liquid and gases.
So they pour the bucket onto the fire and it becomes gas.
No, it's
The explosion. Right? No.
Okay, so they get the water in the bucket, right? But then the people who are playing the role of the matter in this case actually have to move. Somebody fills up a bucket and then themselves walks over to the barn, or runs over to the barn, and throws the bucket onto the fire. Then they run back to the pond, get the water in the bucket, then they run back over to the barn.
bucket is the
Literally said they don't move.
So the bucket.
Say again?
You said they don't move.
In conduction, they don't move.
Wait, so like different scenarios.
Maybe this is a bad example.
Yeah.
That was kind of the point of this, right? That there were 3 different situations that we had to illustrate.
So like this.
I have a question.
So,
That's what I thought.
Like with that.
what do you want to draw?
Like the way it works.
I just explained.
Alright, so I was right when I said the people putting the water on the fire.
I guess I didn't understand that from your dad.
How do they
Yes, Matt.
It's the last day of school because me and Jafar are having an argument currently.
I believe it's June 8th.
See, it's not the second. Where do you get the second?
It's definitely not the second. It's later than that.
You said the 9.
All right. Hey, I'm glad we're focused on what we're doing here.
How is it plausible for them to get the water all the way up there without running through the barn to get up there to throw the water on the fire? And at that point, why don't they just open the doors and like get the cows to run out?
Barn still burns down.
What?
Barn still burns down.
You build a new barn. It was probably
I
old
mean,
and
you don't
rotting.
have to build a new barn.
It was probably old and rotting anyway.
All right. So,
You could light on fire that easily.
all right. Hey, this is not a productive conversation. At least,
As if we really have
as
productive
these, even though these scenarios were ridiculous, they were at least related.
So literally spent a half hour listening to our favorite cereal in class.
Yes, and now we're behind, so now we have to do this. So. All right. So, conduction, right? Conduction is based on contact, okay? Meaning, conduction in gases is slower than in solids or liquids. Why does conduction happen slower in gases than solids or liquids? They're really far apart, right? If we look at the representation of the particles based on kinetic theory of matter, right? Even though the gas particles move quickly, they're really far apart. So conduction in gases is slower than in solids or liquids because the particles are really far apart and they collide less frequently. Example. Sorry, finish right. You can paraphrase if you want to. Preferable.
That's fine.
Sorry, that's the last grade of this protocol. What?
No, it's on Tuesday, the day before the end of the quarter. Gosh.
I swear you're not surprised. You did not get 33 on your AC1. That's what your AC1 is. And you did not get 33 on
But he does know that we go over the calendar at the beginning of every class.
Yeah, dude. Whoa.
Yeah, but you never said it.
He's asking me about one of
I never even took
Well,
it.
I mean,
All right, so
Did you get a 53?
question. Styrofoam.
You guys really having a good time too?
I wish you weren't so we could do this. So. All right, so a styrofoam cup. Okay? A styrofoam cup has a very small density, right? Because a styrofoam cup, even though it's a solid, has a lot of air mixed into it, right? It's very light, there's a lot of air pockets, okay? You put something hot in a styrofoam cup, but then you can pick it up with the cup. Because most of the styrofoam cup is what? Air. Does the heat transfer or conduct through the styrofoam cup? Does it feel as hot as the stuff inside? Right? Okay. It does, but it doesn't conduct as quickly as if it was if the hot liquid was in direct contact with your skin, right? That air that is in the styrofoam cup slows down the conduction of energy from the hot drink to your fingers. Or if you go to Starbucks, right? Even if you don't go to Starbucks, I think everybody's probably seen Starbucks before. You know that little cardboard slider thing that they put on your cup, right? The sleeve. If you look at it, right, it actually has like 2 layers, and one of the layers is like twisted and bent and stuff like that into a bunch of different like little rings, right? Inside each of those folds in their bend is a bunch of what? Air. So what does it prevent from happening? It prevents heat from going from the hot liquid to your hand because it's a bunch of air that prevents conduction. Okay? All right. We will pick it up from there tomorrow. All right. Finish up our conduction, or finish up our heat transfer, and get into calorimetry hopefully.
So we didn't get much done today.